I wanted to clarify the two different conventions that are commonly used for second-order reactions of the type 2A going to B. In the first convention, which is the one that we use in class, we defined that the rate is equal to the appearance of product B over time. Since 2A's react for every B that's formed, this is equal to half of the disappearance rate for A. We define this whole thing, as with any rate law, as equal to sum K times the concentration of A squared, because this is an elementary reaction. I'm going to call this K, K1. If we were to integrate this equation, we would find that 1 over the concentration of A is equal to 2 K1T plus 1 over the initial concentration of A. Here, these concentrations of A are the full concentration of A in the solution. In the other convention, rate is defined as the disappearance of A over time. This is then equal to double the rate that B is appearing at over time. So we say this is equal to some rate constant, which I'll call K2, times the concentration of A squared. If we were to integrate this rate law, we would find that we'd get 1 over A is equal to K2 times T plus 1 over A naught. By comparing these two different conventions, you can see that what's different is we've defined our rate differently, and so our rate constants are different, but they're very closely related. 2K1 is equal to K2. So you'd get a different rate constant depending on which convention you use. So now let's look at what happens if we graph. In this first case, if we make a graph of 1 over the concentration of A versus time, then we might get something that looks like this. And this slope here is 2 times rate constant K1. So we can see from here that we get a linear plot with the slope of 2K1. In the second case, we make the exact same plot, and if again we're plotting 1 over the concentration at A, in both cases these are the full concentrations of A, we'd expect to get a line that's identical with the same slope. However, here we'd call our slope K2, which is equal to K1. So they have the same slope, but we've defined our rate constant differently. In the first case, if we wanted to have a plot that gave us a slope with our rate constant K1, in that case what we'd need to do is plot 1 over half concentrations of A. And if we did that versus time, what we'd get is a line that had a slope equal to K1. Now let's look at how we'd calculate rate constants and how we'd calculate half-life in both of these cases. In the first convention, we have that our disappearance of A over time is equal to 2 times K1 times the concentration of A squared. So if we were given the rate of disappearance and if we were given the concentration of A, we would need to factor in this 2 when calculating our rate constant K1. In the second case, we have that the disappearance of A over time is equal to K2 times the concentration of A squared. So if we were given a rate of disappearance and we were given a concentration of A, there would be no 2 involved. We could simply just plug those numbers in and get this K2. Now for half-life, we'd find that T1 half in this case is given by 1 over 2K1 times the initial concentration of A. This is the full initial concentration of A. And in the second case, we'd have that the half-life is equal to 1 over K2 times the initial concentration of A. Again, the full initial concentration of A. If we review that 2K1 is equal to K2, we can see that these half-lives are going to be identical because we could replace this 2K1 with K2 and we'd have an identical formula. And that makes sense. It shouldn't matter which convention we choose. The reaction will take the same amount of time to go from its initial concentration to half that concentration. So those are the two different ways that we can look at second order reactions of this type. You'll get a different rate constant depending on which convention you choose. You just need to be clear about which convention you're choosing by showing what you're defining as your rate and your rate constant. And then once you choose a convention, just make sure you stay consistent with it throughout the problem.